Hey everyone, welcome back to Chem Story. Today, we're going to talk about one of the most important ways to represent molecular structures in organic chemistry, the skeletal structure. It's a quick and efficient method for visualizing complex molecules, and it makes it much easier to analyze and understand how those structures are put together. Out of all the ways we can draw molecules, skeletal structures are by far the most commonly used, and that's because they're just so simple and clean. Skeletal structures are everywhere. You'll see them in textbooks, research papers, lab reports, and even in industrial settings, like pharmaceutical research or chemical manufacturing. They give us a clear and concise way to represent molecules, which makes chemical structures much easier to interpret. So, if you really want to get comfortable with organic chemistry, knowing how to read and draw skeletal structures is absolutely essential. One key feature of skeletal structures is that carbon atoms aren't actually drawn. Instead, we assume that there's a carbon atom at every line junction and every endpoint. And because carbon always forms 4 bonds, we also leave out the hydrogen atoms that are attached to it. They're just understood automatically. The only time we actually draw hydrogen atoms is when they're bonded to heteroatoms, like oxygen, nitrogen, or halogens. To convert a Lewis structure into a skeletal structure, the first thing you want to do is identify the carbon backbone, whether it's a straight chain or a ring. Then you replace the explicit carbon atoms with line junctions or endpoints. Because skeletal structures are meant to simplify things, we leave out both the carbon atoms and the hydrogens attached to them, since those are understood by default. This makes the structure look cleaner and much more efficient, while still keeping all the important information we need. Only heteroatoms, like oxygen, nitrogen, and halogens, need to be drawn explicitly in skeletal structures. Once you get the hang of it, skeletal structures make it way easier to read, interpret, and even communicate molecular information in organic chemistry. Alright, let's jump in and start practicing how to draw some of these. The diagram shows how to convert a Lewis structure into a skeletal structure. First, you want to identify the main carbon framework, and in this case, it's a straight chain made up of 6 carbon atoms. Instead of drawing each carbon explicitly, skeletal structures use line endpoints and vertices to represent them, which creates that familiar zigzag shape. Since carbon always forms 4 bonds, any missing bonds are just assumed to be filled in with hydrogen atoms, which is why we don't draw hydrogens connected to carbon. If the molecule only contains carbon and hydrogen, just connecting those zigzag lines is enough to show the entire structure. It's a really fast and efficient way to represent molecules, but even though it looks simple, it's really important to understand the hidden details within a skeletal structure so you don't miss anything when interpreting it. Now let's take a look at cyclic compounds. This diagram shows how to transform the Lewis structure of cyclohexane into a skeletal structure. In the Lewis structure, each carbon is bonded to 2 hydrogen atoms and 2 other carbon atoms, forming a 6-membered ring. But in the skeletal structure, we only show the carbon-carbon bonds, which simplifies everything down to a clean hexagon that represents the entire cyclohexane molecule. Next, let's see how to convert compounds that contain heteroatoms. In this example, the carbonyl carbon is assumed to be at the bond intersection, and the CH3 group is shown as a simple line extending from it. Now remember, heteroatoms and any hydrogens attached to them must be drawn explicitly in skeletal structures. So the carbonyl oxygen and the NH2 group both stay visible. This way, the skeletal structure stays clean, but still gives us all the essential information we need to interpret the molecule correctly. Now let's take a look at compounds that have multiple bonds and cyclic skeletons. As always, carbon atoms are not shown, they're just assumed to be at the vertices and endpoints of the lines. But any oxygen atoms still need to be drawn explicitly, since they're heteroatoms. Triple bonds and double bonds are drawn with the proper bond angles, just like you'd expect in a real structure. And again, hydrogen atoms attached to carbon are omitted, because we can just infer them based on carbon's valency. All of this comes together to give us a clean skeletal structure that still accurately represents the full molecule. To convert a condensed structure into a skeletal structure, you can follow these 4 simple steps. First, take a look at the condensed structure and figure out how the carbon atoms are connected, whether it's a straight chain, a branched chain, or a ring. Second, Replace the carbon atoms with vertices and endpoints and draw the carbon-carbon bonds as zigzag lines. Third, leave out all the hydrogen atoms, since those are automatically inferred based on the number of bonds each carbon should have. And finally, always remember to include any heteroatoms, like oxygen, nitrogen, or halogens such as fluorine, chlorine, bromine, or iodine. These same rules also apply when you're working with cyclic structures. To convert the following compound from condensed form to skeletal form, start by identifying the main carbon chain. When you see moieties enclosed in parentheses at both ends, go ahead and leave them out at first and focus on figuring out the core carbon backbone. Once you've got that structure, you can go back and reconnect the terminal groups. In this case, the main carbon chain has 4 carbon atoms, with 2 methyl groups attached, 1 at each end. For another example, let's start by identifying the main carbon backbone in the given condensed structure. The 2 CH2 groups in the leftmost parentheses are actually part of the continuous chain, while the 4 CH3 groups are methyl substituents. The longest chain here has 8 carbon atoms, and we number them starting from the right end of the chain. Replace the carbon atoms with vertices and endpoints, and draw the main chain as a zigzag line. Then, just add the branches where needed, 2 methyl groups at carbon 5, 1 at carbon 4, 1 at carbon 3, and a bromine atom at carbon 2. Since carbon forms 4 bonds, we can leave out the hydrogen atoms, but the bromine, being a heteroatom, stays visible. The final skeletal structure gives us a clean and simplified view of the molecule, but still keeps all the important details. And that wraps up our discussion on skeletal structures. We've talked about why they matter, how to read and draw them, and how to convert different types of structures into skeletal form. Mastering this skill will make organic chemistry so much easier to understand and a lot more fun to work with. So keep practicing, and pretty soon, drawing skeletal structures will feel like second nature. Great job today, and I'll see you next time.